Yeah, perfect, because you said subgroups of Lie groups, and that's exactly my point. So usually people, when they read this title, they read subgroups, and I'm going to think about subsets. And that's, yeah, I mean, thank you. Like, it wouldn't have been better. So yeah, that's what I'm going to talk about today. I'm going to try to say something about this discrete subset of Lie groups. So in a sense, subgroups are periodic, because they are subgroups, and subsets are slightly less periodic, or I'm going to think about some that are slightly less periodic. Okay. Since like I don't want to consider all subsets because it would be way too much, I'm going to just like give you a few pointers so that you have an idea of what I'm going to look for. Obviously, subgroups are fine. I mean, subgroups are amazing. Lattices in Lie groups are just a really interesting topic. And so the example you can keep in mind for really regular subsets by Zn into Rn, or just SLN Z into SLN R. They're perfect, they're amazing. Another slightly more funky, slightly less regular subset of Lie group here, it could be R2 or the hyperbolic plane, is what I call the vertices of Penrose tilings. So Penrose tiling is essentially a tiling in general is you have a few polygons, a finite number of polygons, and you tile the whole plane using them by translating them. Penrose tilings are examples of such tilings that are very interesting for lots of reasons. And when I say vertices, is each of these polygons will have a number of vertices, and you just like look at all the vertices you have in your plane. It gives you a really nice, really well spread subset. So that's a type of subset I want to look at too. And the last one is maybe for the more number theoretically minded people here, and it's what we call the Piso numbers. And so the Piso numbers, if you want to say it quickly, are the numbers such that all of their Galois conjugates, the algebraic integers, such that all of their Galois conjugates have a norm smaller than 1. Okay, so I'm going to be a bit more specific than that. I'm going to look at the Piso number of one field. So I have a number field in R. I guess it's a real number. And what I'm looking at is this set. So the set Piso K, which is the set of the X that are algebraic integers that are primitive in the sense that they generate the number field. And such that if I take any Galois conjugate that is not X, then the norm is in the usual absolute value of R is smaller than 1. Okay, so it's a really interesting set that's discrete and that has lots of interesting properties. And if you want to generalize that a little, you can take the same number field, you can take a finite subset of places and look at OKS in the restricted added ring. And here by OKS, I mean the places where the elements of this thing can have norm greater than 1 is exactly S. And S might not contain all of the infinite places. So this might not be a ring, but that's the interesting thing. Okay, so what do all these sets have in common? So that's what I'm going to explain. And essentially, one set of properties they share is they are all, almost all except for the Penrose tiling in H2, they are all Meyer sets. Okay, so Meyer sets were defined by Meyer, Yves Meyer, and you can define them like that. So you take lambda, it's a subset of A, and A is a locally compact abelian. Let's start with abelian group. Okay, and you will want your lambda to satisfy a series of properties that will be a bit like that. So first of all, you want it to be discrete, and slightly more than that, you want it to be uniformly discrete. And this property is relatively easy to define. You take W, any neighborhood of the of 0 in your A, and you say, okay, if I have lambda 1, lambda 2 in lambda that are distinct, then they are quite far apart. So you can say that way. Lambda 1 plus W is okay, intersection with lambda 2 plus W is equal to empty sets. Okay. So here the notation lambda 1 plus W is just the standard. I'm translating W by lambda 1. Okay, that's the first property. I want them to be uniformly discrete, but I don't want them to be too scattered. And for that, I'm going to ask them to be relatively dense. And here again, what does it mean relatively dense? Essentially, I want that any point of A is going to be within bounded distance of some point of lambda. And by that, I mean the easiest way to say it is I take K in A, which is compact. So there exists K in A compact such that lambda plus K is equal to the whole of A. Okay, and this notation here just means that I take all of the sums of one element of lambda and one element of K. Okay, so it's the Minkowski sum as it's okay. And the last property, because here is if you just have these two properties, it's actually quite, I mean, you could have almost anything. It's really wide. Well, you're going to ask for some sort of like additive combinatorial idea, additive combinatorial property, and that's the following. So you're going to ask that it's an approximate subgroup. Okay, so this property can look a bit odd at first sight, and it says the following, that there exists F in A, which is a finite subset, okay, such that if I take the Minkowski difference, it's not much larger than the set you had originally, and by not much larger, you mean that it's essentially controlled by this small set F. Here, what do I mean by lambda minus lambda? I just mean the set of all the differences of two elements of lambda, and here I mean the set of all the sums of one element of F and one element of lambda. F being small, because compared to lambda is infinite, so being finite is small. You see that what that means is that the difference is not much more than the set itself, and so you can see why, for instance, Zn is obviously a Meyer set. It satisfies all of these properties quite easily. For the Penrose Silings, it's slightly more difficult. It's like results of the brine, and it's a bit more involved. And for Piso numbers, well, you just have to look at it the right way. But I'm not going to say more. Okay, so what was really interesting?
That these are numbers altogether or in a fixed field?
In a fixed field. Yeah. Altogether, it's too much. But if you have a fixed field, you have a really nice Meyer set. Okay, so what makes these sets really interesting? So first of all, they have, geometrically speaking, they're quite interesting. They can be defined. So this definition here, this last condition can be a bit odd, but you can replace it by Fourier analytic conditions that make more sense. Or as I like to say, so a theorem of Lagarias tells you that essentially they can be seen as the subsets that can be well pixelized. You can pixelize them without losing too much information. I'm not going into the details. Anyway, so they're interesting sets, but also they enjoy really nice characterization that was proved by Meyer in 72. And so I'm just going to draw it for a Meyer set in R, so I'm just going to stay with one-dimensional things. And what Meyer said is that the only way to produce Meyer sets in R is the following. You start with a lattice, so here is my integer coordinate grid, in a higher dimensional space. You take in that grid a line, okay? And that line is going to correspond to the set R that I have here, okay? And I take something, maybe the orthogonal line or just any transverse line, and this is supposed to be the origin, but I missed it, but you can see what I mean. So you have these two lines, and what are you going to do? You're going to do what they call cut and project, which means you're going to cut a strip along this first line. Okay, that's a nice strip. It's just two parallel lines. And you're going to select all the points that fall within that strip, all the integer points that fall within that strip. Okay. And what do you do with them? Well, you have a transverse line, so you can just project them on this orange line, and you get like that. As you can see, a nice uniformly discrete subset of my line R, and you can see that it's in fact a Meyer set. It's not too difficult to show. And in fact, Meyer proved that this is the only way to construct Meyer sets. So you might have to go to higher dimensional space, maybe with n as large as you want, and this works also for lambda in Rn for n as large as you want, but essentially that's the only way you can do it, and that's called the cut-and project. Okay.
Can I ask a question?
Yeah.
So is the number of dimensions that you have to add related to how large is the set F?
Yeah, it is. So essentially, heuristic essentially is that the log of the set F, the log of the size is going to be the dimension, roughly. There's a trick, but roughly. Okay, so everything is fine so far, but we have just addition, and I talked about sum product. So I want to throw in a second operation, which is just going to be the multiplication, and we're still going to talk about theorem of Meyer from the same time. Okay, which says the following. So we have to restrict to things that are in R, and we are going to ask that lambda is uniformly discrete. In R, you don't really need this condition because R is too small, but essentially what you're going to say is that first lambda is a Meyer set. Okay, so this is enough, these two conditions in R are enough to say that it's a Meyer set. And you're also going to say that it satisfies the same thing for the multiplication. So here, well, just going to write dot lambda is just the set of products. And I want it to be not too much bigger than lambda itself. So here there's a weird thing where I use the addition here, whereas you might want to use the multiplication. I think it's roughly the same, but I've never checked it. So if you have these two conditions together for some f finite, what happens? Well, essentially, there exists k in R, a number field, such that lambda is roughly the Piso numbers of k. Okay. So why do I find this theorem really fascinating? Is because you have these, well, two kind of, it's the classic. You have the interaction of the sum and of the multiplication, and out of that you get a really precise number theoretic description. Essentially, you have one possibility, you're the Piso numbers. And when I say roughly, I don't mean that you have to rescale R by something or anything. It's really what might happen is you might remove like a small number of points from Piso k, and you still obtain something that's like that, but you can only just remove or add a little, but not much more. Okay, so
assume the relatively dense property here.
Yeah, that's the trick of R. You don't need to in R. In R, you're either finite or if you're uniformly discrete, and that you're either finite or relatively dense. Just to make the theorem look a bit more general, but it's not. Okay. So that's something very fascinating, and in fact,
what if lambda could be finite then?
Oh yeah, it needs to be.
Yeah, I mean lambda could be finite. It satisfies all those.
Yeah, it needs to be infinite. Yeah.
Okay.
Yeah, it's either finite or that. That's it. Yeah, good point. Thank you. Okay, so what does it point to, this sum product theorem? Well, what it points to is that there might be a similar phenomenon happening in non-commutative groups. And what do I mean by that? So I'm going to express a theorem, but essentially all of this can be restated in non-commutative groups quite easily. What you do, you replace this minus here by multiplication, up, and you forget about the abelian. And what you might want to do for convenience is ask that you have a set that contains all of its inverses. So all of a sudden I have a perfectly nice definition that works in the non-commutative groups.
Towards one direction. In the sense that lambda times k may not be k times lambda.
Yeah, that's exactly why I ask that you have the inverse.
You're assuming that.
But that's a very good point. Otherwise you have okay, and so the big question for some time was, we have this really nice arithmeticity property with these two approximate group kind like property, you obtain some arithmeticity condition. If I have that, do I have the same? And the short answer is yes. So let me explain. So it's the collection of a bunch of results. So I'm going to start Rashowski with work in 2020 and myself with work in 2018, 2020. And 2022, which says the following: if you have lambda, okay, so my non-commutative Meyer set in a in an algebraic group, in a linear algebraic group. So I want it to be linear.
Why are you calling it some product? It's just product, right?
Some product here?
Now there I see, but in the pure group theoretic setting.
Oh, here in the pure group theoretic setting. Well, when you have good non-commutativity, you have two operations.
No, but it's just the theorem is just about products. The definition just involves products, right?
Here for the Meyer set, yeah. Yeah. So if you have in a linear algebraic group H, let's say, essentially you have that lambda is something like, okay, and so what are all of these? You have, okay, a number field S, a finite set of places, and H is just a K linear group. Okay, and what does it mean to take H of OKS? Well, H is going to be linear, so it's in GLN, in some GLN, and you just take the points with entries in OKS. Okay, and so what's nice is you find again. So as I said earlier, these things are just, when you think about it, a generalization of the piece K. And then you find again this very nice property that like simple, maybe, well, here just with multiplication, as you said, conditions will imply a strong arithmeticity property. Here, this almost equal depends a lot on exactly the conditions you have on H, but it always comes from this construction there.
So what do you mean by inner linear algebra group in its real form?
And it's overall it's over a local field in the points over the local field. So
you don't take a product of local fields.
Yeah, you can. So it turns out that, and there's a nice thing where when you have local fields of characteristic, of positive characteristic, actually anything that's approximate is essentially already a group.
So approximate means up to a finite set. What is
it? Yeah, it's this Meyer set. This Meyer set property. So if you have a Meyer set and your fields have positive characteristic, you're not inventing anything new. You just have like already a group. But in characteristic zero, then you have this new type of objects.
So what is ruling out a non-arithmetic lattice?
Pardon?
What rules out a non-arithmetic lattice is an example of a Meyer set?
Oh yeah, so that's the thing. So you have what I mean by this roughly is that the few exceptions to being arithmetic are essentially the non-arithmetic lattices in rank 1.
Yeah.
But you don't have anything approximate. It's just already a lattice. No, it's not. Yeah, and that's it essentially.
Okay, that is an example of a Meyer set, right?
That is an example of a Meyer set. It's not arithmetic, but it's what I mean is there's no new example.
Okay.
The only way to be non-arithmetic is to be in the world of lattices already.
Is that one thing that I think Meyer did was explain these tilings, right? This cut and whatever you called it, cut and project is a way of explaining the Penrose tiling, right?
I think it's De Bruyn who did that with this.
So do you have the analog of tilings of that theorem, that aspect?
So yeah, well, what you could do, yeah, you could just take the Voronoi. You can define just like in the outer case the Voronoi cells around the points of your group of your lambda, and then you get effectively actually a tiling with a finite number of subsets of your whole thing. And this tiling has nice periodicity properties, but yeah, I haven't managed to make it strongly periodic. For instance, it's only weakly periodic or things like that. Yeah. So that's the thing. And if you want to hear more about that, or why you should care about these things, or why it's interesting, I'm going to give a talk in 1 month here with a bit more time and a bit more details.
Ever use the sum product techniques of that Bogan loved so much?
Well, this
Like if you have an approximate subset which is closed in a ring, you know, like the Erdos conjecture that was solved, I forget by who. And you use those techniques, or using you are using arithmeticity theorems or?
No, it's more arithmeticity theorems and actually just techniques that are more like this, what proves this theorem of Meyer. Actually, these two theorems are rather elementary to prove, and it's more this kind of philosophy, which is in simple groups. What it boils down to is you look at you have your torus, your split torus, and you look at the root subgroup, and you let the split torus act on the root subgroup, and it creates some arithmeticity. There's something that's well known, but it's just trying to show that there's a philosophy behind it.
But you're not using any aspects of a subset which is closed under multiplication and addition, almost closed some structure.
You do use some things. Nothing too deep actually, because it's quite different. The point is these sets are really big, so you don't have any good way to measure their size. And most of the things that were developed were for like finite, or maybe you have a small measure or something, like that, and you don't have it at there. So periodically, at some precise point, you use similar techniques, inspired, but maybe the whole philosophy is slightly different. Maybe erase that. I don't know if the next one is using the board.
So this H is different from the H, which was lambda was a subset of H, right? This is possibly a different H.
It's possibly a different H, but this, but they should agree essentially when you take. So when you take. So if you look at H of A. KS, essentially, you should recover the H you had originally. So there's a lot hidden there, because obviously you can't do that all the time. But it always comes from that construction in a very specific manner. You can really trace it back to that construction. Okay. Thank you very much.